simple this equation. This is the two-body problem. And then we derive an expression for R, which is the scalar projection. This is the trajectory equation or the solution to two-body problem. Now, this is also referred to as Orchard equation or trajectory equation. And we also looked at definitions of this is specific angular momentum. Okay. And we know H is constant. Okay. So we showed starting from mu over R cube, R is equal to 0. Show that V over dt of R implies H is constant. Okay. And we also looked at starting from zero, show that V square over 2 minus mu over R is equal to epsilon, or d over dt of V square over 2 minus mu over R is equal to 0. So this is this dy equation or in this equation. Okay. What we can do today is let's look at Kepler's laws of planetary motion. So Kepler stated 3 laws, all right? And the first law states that planets follow elliptical paths around the sun. Okay. The condition is, this is important, with sun being at one of the foci. Okay. The second law states that second law states that planets orbiting around the sun trace equal area in equal times. And the third law
on the second line, it says haste.
planets orbiting around the sun trace T R A C E. Okay. I'll talk about these laws.
What's the last word?
Foci. I'll talk about what a foci is. Yes.
Right under the orbit equation, you have H, R cross R. What's right after R dot?
Anderson. And. H is constant. Alright. Last law, the orbital period of a planet is proportional to the cube of its mean distance. Alright, so let's talk about these a little bit here. So let's discuss orbits Alright, I need you to pay attention here, okay? We're going to discuss orbits in the context, all orbits. How many orbits did we identify? How many types of orbits did we identify? Four, right? So we are going to discuss all of the orbits in the context of a elliptical orbit, okay? And it will apply to all the rest of the orbits. Okay. Now, how do you draw an ellipse? Does anybody remember drawing an ellipse? Or have you attempted to draw a perfect ellipse? So what you do is, you take 2 points, okay? You insert 2 pegs at these points, tie a string around it. You got it? And then trace it. Trace it. So
You put a loop around the 2 points. You just push it out until the string is tight.
So what you do, yeah, so you have 2 pegs like this, right? And you put a string around these, okay, or a loop. You understand? You stretch the loop, you keep stretching the loop and you draw this like this. Get it? That's how you get an ellipse. Does that make sense?
Show it again.
You have all right, come on here. First. Hold this. Okay, hold this here. So this is my loop. You got it? This is stretchy, but we don't generally go with a stretchy this thing. Okay, it should be loose.
It should be like
It should be tight. Okay, it cannot be tight. So keep your thing.
chilling its brains.
You see this? If I do this, you with me? Mm-hmm. If I do this, hold it tight. If I do this, I'll get an ellipse in this path. Does that make sense? Are you able to see it? Hold it tight.
Are those supposed to be pilot arms?
What I'm going to do is I'm going to take something like this. Hold it tight. You get it? It will place an ellipse. You get it? Right. So,
Hey, Adrian.
I know you
Yeah.
guys are doing it all. You know.
At this point, that's your recommendation. Oh, I got it.
you do this. You see that? If you trace it, you'll get a ellipse. You understand? Does it, you get the idea of how to draw an ellipse, right? If I complete this, these 2 points, what I'm trying to signify is these 2 points are very critical. All right? Those are the foci. Does that make sense? One of them is focus, right? 2 are foci. One of them is locus, 2 of them are loci. You understand? There is no locuses or focuses. It's foci or foci or loci. Okay?
So,
Plural, yes.
do they have like names or not?
Huh?
Do they have names like or not?
What name?
The foci. Do they actually have names?
Foci, that's what they are called.
So they don't have like a different name to tell the difference between. That's what I'm asking.
Yeah, we'll get to that.
Okay.
Do you get this? Guys, pay attention here. If you have, so we are going to, these 2 points are very critical. They do have names, Julian mentioned.
Okay.
This is your ellipse. The thing is, these 2 points are equidistant from so if you have one of the foci is here and another here, this distance is same as this distance. You get it? Now, what's going to happen is what it says is the first law. Planets follow elliptical paths around the sun, with sun being at one of the foci. What that means is planets will go around like this. You with me? Where is the sun? Huh? It's at one of the foci. It is not at the center. This also has a center, but it is not at the center. You get it? Guys, I need you guys to pay attention here. Okay? Don't take notes or don't try to read anything. You're going to miss this. I have graded exam 1. You have not done well. Please pay attention.
I have 2 questions. So what's the loci again?
Locus is again a path.
It's just the fact.
Yeah, focus is point.
Okay. Also another question. How do you know that string thing makes a perfect ellipse? How do you know that? Is that just
If it's not stretchy, how do you do a circle? You just hold it like this, and if you take one string and do that, you'll get a perfect circle, right? Similarly, if you have 2, you get a perfect ellipse. You got it?
So what if you have 3?
You should try that. Alright, this is how you draw an ellipse, and it's critical. Again, what we'll do is we'll limit the scope of how many points we have, how many pegs we have with respect to what is relevant here. Okay. So these two, this is where the sun is. Always keep in mind. So this is called the occupied focus. This is called the unoccupied focus, right? Because what is here?
Sun.
Nothing.
Sun.
The sun is here, right? The sun cannot be in two places. You understand?
Right.
So this, what is this path?
It's the path of the orbiting
Path of the
body.
orbiting body of the planet. Okay. As these 2 points move closer and closer and closer, this orbiting path will tend to become a circle. You understand? When these two foci are at the center, it becomes a circle. So in the context of sun and planets, these two foci are very close to each other. Okay? It's almost a circular orbit, but it is, strictly speaking, it's an elliptical orbit. You got it? Does that make sense? So this is where the foci is. Alright?
Alright, question. So you're saying focuses, but what do you mean by focus?
Focus is these 2 points, those 2 points at the peg.
And
This is
foci
where the sun is.
And foci is just one of the points.
Foci is 2. Focus is 1.
Okay.
This is the occupied focus, F. F star is unoccupied focus. There is nothing here. Alright? And this is the path of the orbiting body. This is what the first law says. Alright? Second law. Planets orbiting around sun trace equal areas in equal time. What that means is, so let's say the planet at T, or let's look at the satellite here. This is a position let's say R0, okay? This is R1. This is R2. You understand? What is R0?
Would it be like your reference point?
It is position of orbiting body
Relative to the sun.
Times 0.
at time t equal to t0. You get it? R1 is position of orbiting body at yes t equal to t1, and similarly RT is position of orbiting body at t equal to t3. Now think about this area. Let's say this area is A1 or dA1, and this area is dA2. What the second law says is dA1 divided by T1 minus T0 is equal to dA2 divided by T2 minus T1, which is equal to dA1 plus dA2 divided by T2 minus T0. Does this make sense? It is tracing an area, right? When the planets, so this is how the planets are going, or the orbiting body is going. Okay? It's doing that this. When it does this, it is tracing area. What is this region called? It's sector. You with me? So the area, if this is the area, dA1 is the area traced in time, T0 minus T1, T1 minus T0, and this is the area traced in T2 minus T1. This is always equal. Equal areas in equal times. You get it? So what happens? That conversely, what it means is when it is closer to the to the central body, it is moving faster. Okay? When it is farther away, it is moving slower. Does that make sense?
Oh, it appears to be.
Hmm?
It appears to be.
Right, because what happens is, what is the area of a sector? Sector.
So that's a sector, right? So DA.
How do you calculate the area of the sector? Formula. It is essentially, think about this as a triangle. It will be base into height. You understand?
That should be arc, right?
Base would be not r. Base would be this arc. R theta. Okay? So the base would be the r, and the height would be the r, the various r. Okay? What do you know about this r? This r is the smallest when it is the closest, right? It is the farthest when it is the largest when it is at the farthest. So if your this base into height should be the same in same area, same time. So this, if this is smaller, to make up for that area, it has to cover more base. You understand? So if you think about this, if you have this, if this is your triangle, right? If this is your triangle, if you want the area of a triangle like this to be the same as this, you need to make this longer. You understand?
Yeah.
So this is the arc. This is the height. If this height is smaller, it has to cover more distance to make up for that equal height. If this height is large, it has to cover only smaller distance. Okay? So that is what this law means. That is what this law states.
Can you just to clarify?
Huh?
So just to clarify, so if you were to take, if you were to track an orbiting body at different periods of time in at equal amounts of time, so if it was like 3 seconds between each track, the area that it's traced would be equal. Is that correct?
Yes, exactly. So if you took 3 seconds, 3 seconds, 3 seconds, if you calculated the area, it will always be the same. What you're going to notice is this is a representation. So if the time taken from going from this to this is the same as this to this, these two areas are the same. You got it?
Yeah.
Or if these two areas, you can imagine that this area and this area could be the same, right? Because see, this height is much more than this height. So the base has to be, this base has to be bigger than this base. You understand? So it has to cover, this base has to take the same amount of time as this base. So it will go faster here and go slower. This could be 3 seconds, this could be 3 seconds. Does that make sense?
Yes.
So, what determines if satellite is going faster, closer to it, slower, farther away? Is it the area or is it arc? Because if the area is the same, then what makes it go faster or slower?
So if this area and this area is the same, right? So this area, compare this to this triangle. You understand? This part is this part. Okay? This part is this height. You get it? This is this, and this height is this.
Right. Like, so,
Now these two areas are the same. Assume DA1 and DA2 are the same.
right, but since the arc on R1 is longer, shouldn't it be going faster than the arc at R9 since it's small? Because it has to cover that same.
Yes, so it is going faster here
Yeah, but
than
you,
here.
right, but you said it was going faster from the beginning, like once it's the closest,
When it is, this is the closest point.
right? That's the fastest.
That is the fastest. This is the farthest point. That will be the slowest.
Okay, so so R1 will be faster than R9?
R1 is different. R1 is the
R1
radius.
Okay, let's say.
Yes, so this should be slower. You understand?
I see that. I just don't see the two argument, the first two arguments. You said that the first one is the fastest, or the one that's the closest is the fastest. But as the picture is drawn, it looks like the R9s have a smaller arc length than R1.
R0 is the height.
Well, I mean the arc length of that.
This is the arc length.
Right. And it's two different ones. I'm saying the arc length is.
Huh?
I need to show you.
Sure, yeah.
I'm just saying, like this one's this one's larger than that one, so it should theoretically go faster because it has to cover more arc length.
Right. So let's only look at these two.
Okay.
These two. Okay. So here we are not talking about this. So the two areas under considerations are this one and this one. Okay. Or you can compare this one and this one to get a better idea. Here and assume that the area here is same as area here. Okay. This sector area is the same as this sector area. Alright?
I see that.
So this is the second law. Alright? The third law, what is the time? It says square of the orbital period. What is orbital period?
How long it takes to get back to zero.
Right, so if the satellite goes from this point and comes back here, okay, that is one orbital period. It is represented by t. T square is proportional to a cube. A is the mean distance. You see the distance is changing, right? This R1, this R is changing. You understand? This t square is proportional to a cube. You understand? This is the third one. A, I'll talk about this A. This is the mean distance, but in this such a case, it will be the semi-major axis. Alright? We'll talk about this. But understand these laws. These are going to be, I'll ask these laws in your midterm. Let me quickly distribute your exams.
First question.
Anything? Riley? Joshua? Marquis? Marquis is not here? Michael? Ryan? Wellington? Ruby? Timothy is not here? Ian? Bukari? Speaker from Bukari? Come here. Marcus? Jordan? Who is this Jordan? He's only taking the exam and can somebody ask him to meet me?
Yeah, definitely.
Rainer? Rainer is not here today? Kenneth? Christian is here? Julian? Akil? I need your exams back. Please don't take it with you. They have not been, have not entered the grades, and don't fold them like Torius just did. You can take pictures if you want. You can take pictures if you want, but don't take them with you.
What's the difference between an 8 and a minus 8? But clearly, I know what
Please give me your exams back. You can take a picture if you want.
He said, no, where did I start? Sorry, it's about two.
I know who are taking the You can take pictures if you want.
No. This is one to one. This is one to one. You made the whole one wrong, but I did it right.
You made a All right. Now, before you guys leave, guys, before you leave, this is not good performance. Okay? I'm going to warn you. If you're, it's like this. It's extremely skewed. You've done decent, or you've really, really gone down. And if you have gone down, take it as a warning. And it is many of you who have not submitted your assignments have not done well. It is clear. Some of you have somehow gotten away without submitting the assignments but still doing okay. But people who have submitted the assignment have done well. People have come to my office have done well. There was nothing new here. You realize that? Look up the assignment. There's barely anything new in this. I pretty much gave you what was given in the assignment. And you still couldn't. There are students who have scored single digits. Not acceptable. You are going to be in trouble. Okay? I don't want you to be in trouble. Honestly, I want you to pass, but you have to change. It's a matter of, this is your character showing, not just your competence. There was nothing new given to you. All you needed to do was solve, do the assignment and take my help to do the assignment. You didn't do it. And see, this is what has happened. Now you don't have any score on assignments. You don't have good score on the exam. You are not going to pass your midterm. You're not going to get a passing grade on midterm.